Welcome to This Explainer. Today, we're decoding a massive, literally planet-sized puzzle. How humanity acts as a catalyst, completely altering the delicate balance of Earth's life support systems. For all you A-level geography students out there, this is absolutely core material. So let's get started. The core idea we're tackling today is how humanity's footprint fundamentally rewires the planet's primary flows of water and carbon. We aren't just passive residents here, you know? We are active agents, constantly changing the underlying math of these global cycles. Here's our roadmap for today. 1. Earth's life support systems. 2. Defining disturb and enhance. 3. Urbanization, concrete and runoff. 4. Farming, soils and storage. 5. Forestry, canopies and carbon. And finally, 6. Restoring dynamic equilibrium. Let's jump in. Section 1. Earth's life support systems. Let's look at what happens when these vast interlocking natural systems are left entirely untouched by human hands. All right, let's start with a crucial concept for your exams: dynamic equilibrium. You know, before human interference, the water and carbon cycles exist in this beautiful state of balance. They aren't static, they're constantly moving. But when a sudden natural change hits, like an unusually heavy rainstorm, it triggers a negative feedback loop. For example, excess water fills the aquifers, raising the water table, which then increases flow from springs until the water table reverts right back to normal. The system naturally and safely restores its own balance. Think of the water balance equation as that natural baseline. Your inputs, like precipitation, have to perfectly balance out against your outputs, which are things like evapotranspiration, streamflow, and vital storage changes over time. When the scales tip naturally, the system simply corrects itself. But what happens when we introduce a highly active catalyst into this perfectly balanced equation? That brings us to Section 2, defining disturb and enhance. Land use change is basically our primary tool of interference. It's the literal process of fundamentally redesigning the Earth's surface. We're stripping away natural, permeable, carbon-rich environments and replacing them with highly engineered human landscapes. Now, this is super important for your exams, so definitely take note. We don't just destroy things. We can disturb the cycles, meaning we damage or negatively alter these life support systems, but we can also enhance them, meaning we actively repair, restore, and improve these cycles. Keep this negative and positive framing in mind as we dive into our case studies. Section 3. Urbanization, concrete and runoff. Our first major case study takes us away from the natural baseline and into the concrete jungle to see how we're completely rewiring the water cycle. Just look at this incredible contrast. On one side, you've got a lush, naturally layered forest canopy acting like a giant, soft sponge, and on the other, the stark, geometric grid of a city like Chicago. We've replaced vegetation and soil with impermeable artificial surfaces like concrete, brick, and tarmac. We have fundamentally changed the surface from one that absorbs life to one that literally repels it. So when we shift from that natural ground cover to high-density commercial areas, where 75 to 100% of the surface is totally impervious, the math of the water cycle just completely breaks down. Infiltration is slashed all the way down to just 15%. And because the water can't enter the soil store, a massive 55% of that precipitation is forced into immediate surface runoff. Now take a second to recall your hydrology basics. As we pave over our natural floodplains and build these hyper-efficient artificial drainage systems, think pitched roofs and gutters, how do we actually measure that rapid shift in water movement? The answer, of course, is flows. In a highly impermeable, completely sewered urban basin, we're blocking infiltration, which drastically slashes the lag time. That's the time between peak rainfall and peak discharge. This causes a dangerous, concentrated, and ridiculously steep spike in peak discharge. We are essentially flash flooding the system's concrete arteries purely because we removed the natural soil and vegetation stores. Section 4. Farming, soils, and storage. Leaving the city behind, we transition to the altered earth of rural farming, where, honestly, both the water and carbon cycles take a massive hit. This visual boundary is just striking. You have this vibrant, ancient green forest abruptly meeting plowed, perfectly geometric farmland. The initial clearance of this forest for arable farming instantly and violently decimates carbon storage. in both the above-ground biomass, the trees, and the below-ground biomass, which is all those root systems. But the disturbance doesn't stop once the trees are gone. Farming is actually a continuous disruption. I mean, the very act of plowing exposes soil carbon to the air, causing rapid oxidation and releasing CO2. When we harvest crops, we're removing organic matter that would normally return to the soil. On top of that, heavy farm machinery physically compacts the earth, reducing infiltration and artificially inflating peak flows on local streams. We're literally attacking the stores while accelerating the flows. Section 5. Forestry, canopies, and carbon. Let's look at our third landscape intervention. This one is a really fascinating practice that plays a highly complex dual role in our life support systems. While ancient, natural forests are a core part of that baseline dynamic equilibrium we talked about earlier, a managed plantation is a totally different story. It's a heavily engineered green intervention, usually tightly packed with fast-growing conifers. Before we dig into the numbers, ask yourself this classic A-level evaluation question. Does planting millions of trees automatically fix everything, or does it actually create entirely new geographical imbalances? Well, it's actually a bit of a paradox. Mature forest plantations beautifully enhance the carbon cycle. They act as massive carbon sinks, holding up to 200 tons of carbon per hectare. That's literally 10 times higher than grassland. But hydrologically, they can be a disaster. Dense evergreen plantations, like Sitka spruce, can intercept up to 60% of rainfall. The water just evaporates right off their needles before ever reaching the ground, severely disturbing local river discharge, extending lag times, and sometimes even causing localized hydrologic droughts that reduce the water yield for public supply. Section 6. Restoring dynamic equilibrium. Having analyzed these catalysts of change, let's synthesize how humanity's footprint interlocks across both cycles. This summary matrix is absolutely essential for your exam revision, so make sure you've got it down. Notice the pattern here. Urbanization and farming predominantly disturb both cycles. They deplete our natural stores and dangerously accelerate our flows. Forestry, however, is a mixed bag. It heavily enhances carbon sequestration, dragging CO2 right out of the atmosphere while simultaneously disturbing the natural hydrology through extreme interception. So, why does all this matter? Well, we've seen the devastating consequences of ignoring this balance. Take the Sahel, for example, where deforestation literally allows deserts to expand southwards because the loss of trees kills soil moisture and regional evapotranspiration. It proves that regional inputs and outputs can be fatally upset. But if we understand the science, we can actively intervene and restore that balance. As you review these complex, beautifully interconnected systems for your exams, I want to leave you with a thought. We now know the mechanics of the water and carbon cycles inside and out. So, will our legacy simply be the disturbance and destruction of these cycles? Or will we use our geographic knowledge to become the master architects of a new, sustainable, dynamic equilibrium? Thanks for joining me on this explainer, and keep studying hard.